All right, the next section deals with what happens when an object is in equilibrium. Equilibrium means everything is balanced. So imagine if you were tugging on an object and trying to pull it. If we wanted to balance out those forces, someone else would have to pull equally as hard in the exact opposite direction. And the way you become exactly opposite is you solve for the resultant just like normal. So draw your triangle, Pythagorean theorem, and then you have to add or subtract 180 degrees to whatever you get for your angle. So if your angle is less than 180, you'll add, and if it's bigger than 180, you will subtract. Okay, so here's an example. We have two forces, 25 newtons. Let's try that again. 25 newtons at 35 degrees and 62 newtons at 60 degrees. So you'll break that into your x and your y. And go ahead and do that. So if you break them into x and y, you should get total x, 51.5. So draw that to the right. Total y is 68. Draw that up. Solve for your third side and solve for the angle. So the magnitude of the resultant was 85.3 newtons from Pythagorean theorem. The angle was 53 degrees. That is your resultant vector. To get the equilibrant, you just add 180 to that angle, and the magnitude stays exactly the same. Okay, when you try this problem, you're going to follow the same steps, but it is not going to be in quadrant 1 when you solve for the resultant. So what you will do is solve for the resultant, check your quadrant, add or subtract 180 or subtract from 360, whatever you need to do, get your final angle, and then add or subtract 180 based on that. So try it and see if you come out with 60 newtons at 98 degrees. The next type of equilibrium problem is what I call stationary sign problems or hanging sign problems. So we have this sign, and it's 168 newtons. That is its weight, and that acts straight down. And it's held up by two ropes, something like this. And each rope makes a 22.5 degree angle with the horizontal. And it is important that the angle is these outside angles and not an in-between angle. And we are looking for the FA, the forces the ropes exert on the signs. Well, the sign's not moving. So we know each of these ropes pulls out, and that's going to be equal. And each of the ropes pulls up. Well, since it's not moving, these two ups have to equal the down, which was 168 newtons. Since there's two ropes, we're going to take this 168 newtons and divide it in half. So that means each rope has to pull up with a force of 84 newtons, and that is going to be the Fy for each one of these ropes. And if we know the y and the angle, we can solve for the Fa. Since y is equal to sine angle Fa, we have 84 equals sine 22.5 Fa. So just divide 84 by the sine of 22.5, and you should get 220 newtons of force in each rope. Okay, question 12, very similar. We have this hanging light, only this time it's supported by 4 chains. And I can't draw this very well, but something like this going in every direction. This time we know the Fa in every chain is 35.8 newtons at 75 degrees. So question A wants us to determine the force of a single chain in the x and y direction. So we're just going to break this into Fx and Fy using your sine and cosine. And then we're going to go to question B, where we're looking for the mass of the light. Well, we have 4 Fy's. We're going to add those all up, and that is going to equal the weight of that massive light. And then we're going to use our equation W equals mg. So we'll divide that weight by the acceleration due to gravity to get the mass. All right, we have one more type of force to consider that acts at an angle, and that's the force of gravity. So if you think about when you're outside sledding, when you sit on a hill, The gravitational force pulls you down the hill. It also pulls you into the hill, and depending on the angle that the hill makes with the ground, that will affect your acceleration. So anytime you have a mass on a hill, we have to break your weight into two components. And those two components are going to be called the parallel and the perpendicular components. And they're very, very similar to x and y. The parallel force is equal to the sine of the angle times the weight, and the perpendicular force is equal to the cosine of the angle times the weight. So anytime you have a mass on a hill, step one has to be take the weight and split it up. You have to break it into parallel and perpendicular. All right, so we have this car parked on a hill. Its mass is 1225 kilograms. So we need to take that and break it into its weight. So first we need to find the weight. So 1225 times 9.8 weighs 12,005 newtons. The two components will always be in these directions. Parallel is always down the hill. Perpendicular is always into the hill. So go ahead and solve those. This one you're going to use sine. This one you're going to use cosine. And after you do that, the weight is now gone. It is split. Okay, and if we look for what this problem is solving for, what is the magnitude, the size of the force, that will cause the car to roll down the hill? And in this case, it's only looking for the parallel component. The perpendicular pulls you into the hill, keeps you from going up in the air. Okay, next problem. You are on a hill. The incline is 24 degrees. You know your mass, 75 kilograms. So change that to weight and break it into parallel and perpendicular. Okay, once you've broken it into parallel and perpendicular, looking back in our problem, we also know mu. Okay, so if we look at this carefully, we know that we're going down the hill. That means the frictional force has to be up the hill, and our normal force comes out of the hill. And it's going to be opposite of our perpendicular, and they're going to be equal to each other. So our Fn is 671.4. We're going to take that times our mu to get our frictional force of about 134. We're going to subtract kind of our rights and lefts, but don't be hung up on right and left because that's determined by which way you draw your hill. Instead, think bigger number minus smaller number. So we've got about 164.7 for our F net, and then we will do that equal to MA. And you get an acceleration of about 2.2 meters per second squared. Okay, we look at Kelvin and Hobbes. They have a mass of 100 kilograms. They have a 29-degree hill. Oh, and their wagon has a mass of 10. So we're going to add those together to get a total mass of 110 kilograms. And they have constant acceleration. Now that is not the same as constant velocity. So we're going to turn that mass into weight. And you're going to break that weight into parallel and perpendicular. Okay. They start from rest, so VI of 0, of VF of 1.5, and they do this in 3 meters, 3.7 meters. So you need to use your VF squared equation to solve for acceleration. So acceleration is about 0.3 meters per second squared. Once we know A, we can take that times our M to get F net. So our F net is about 33.4 newtons. We can use that F net with our down the hill minus our up the hill. And if I subtract the 523 from both sides, both sides are negative, so our FF will be about 490. And our FN is going to be the same as our F perpendicular. So we have FF equals mu FN, so 490 divided by 943, and we get a mu of about 0.5.